to let that picture record for a while.
Just look, I'm just making it work in that picture.
Yeah, the
Tony's
last
looking
time.
for his formula. So,
We
now
yeah, we
recurring
got
problem.
Yeah.
I
All
got the
semester
wrong
long.
screen showing.
Oh, yes. The last time, when in doubt, just put 4. I started reminiscing about something and
Regarding the Vietnam War. Let's get started.
Okay,
We've done most of this stuff from this section.
Okay,
it just
Tim,
seems
let's
like
go
we're
ahead
ready
and
to.
start record. It's recording, so you start reviewing the determinant.
Isn't that what I was going to do?
Yeah.
Okay. So, y'all remember the last step we were doing? We were finding 2x2 and 3x3 determinants. Remember, 2x2 determinants are defined to be the difference of their cross product, AD minus BC. You always start at the row 1, column 1 entry in the matrix when finding a determinant.
What I call the first number.
For a 3x3 determinant, there's a little more involved though. 3x3 means 3 rows, 3 columns. If you remember the trick to see all the different cross products, you have to recopy the first 3 columns. The first 2 columns. Then we have 3 diagonals you multiply down from falling from left to right, minus, then you start falling from right to left for those 3 diagonals. And with that in mind, we're going to start today with something called Cramer's rule.
Oh, you've already written Cramer's rule.
I know it. That's good. You're right, Tim. Cramer's rule uses determinants to solve linear systems of equations. Remember the last time we looked at elimination and substitution? We talked about augmented matrices. This uses determinants. To solve linear systems.
Instead of elimination or substitution.
I'll put that parenthetically. Instead of elimination or substitution. So now you have a new method of solving a linear system.
Going to have a new method. Why don't you tell it to them?
Oh, just for the record, today, April 23rd, 2025, is Administrative Professionals Day. So if you know an administrative professional, this is the day you're supposed to get them something nice, or at least tell them Happy Secretary's Day, something. Okay. Cramer was actually a very prolific mathematician. He came up with all sorts of important discoveries in mathematics. It's funny, something that he didn't think was that significant is the one thing he's remembered for, because it's in every college algebra textbook in the world, this idea of Cramer's rule. Okay. What Cramer did, maybe we should just look at an example.
Yes, show the example.
Oh. So this is number 13. Solve using Cramer's rule. 7x plus 5y, 7x plus 5y is equal to, is that a 3? I want to make sure this number looks different, so I'm going to use a red pen. And then 8x plus 4y equals -2.
I guess if you were going to use elimination, you could make the x's 56 and -56.
Yeah.
Or maybe you could make the y's, what, would y'all say 20 and -20?
I think I'd rather do that. Multiply the top one by -4, the bottom one by 5, and add the two together. So you have 20 and -20 on the y, but we're using Cramer's rule here. Certainly, if they didn't tell me how to solve this thing, one method I definitely wouldn't want to use is substitution, because whether you solve for x or y, in either equation, you're going to be stuck with a fraction that you then have to substitute back in. Here's what Cramer did. The first thing he did was find the determinant of the coefficient matrix. Just the coefficients. Oh, by the way, for Cramer's rule, it's just like elimination. You need the x variables aligned, the y variables aligned. You need the constant terms, the things that don't have variables, by themselves on the right-hand side. So, the first thing Cramer did was find the determinant of the coefficient matrix. The coefficient matrix is just the coefficients on x and y. The coefficients for x are 7 and 8. The coefficients for y are 5 and 4. Y'all remember finding a 2 by 2 determinant? You multiply minus multiply. 7 times 4, that's 28, minus 5 times 8 is 40, and 28 minus 40, is that a negative 12? First thing Cramer did was find the determinant of the coefficient matrix. And in this case, it turned out to be negative 12. Any questions up to this point? Then he found a new determinant, one that he denoted d subscript x. D sub x. D sub x is the determinant you get if you replace the x column. You're replacing the x column with the column of constants, 3 and negative 2. The y column stays the same. You're only replacing the subscripted column. The x column becomes the column of constants, 3, negative 2. The y column stays at 5, 4. And remember, multiply minus multiply. 3 times 4 is 12.
Oh, this is good.
Minus, what am I going to get for this cross product here? Negative 10. Watch those double negatives. 12 minus a negative 10, that's a 12 plus 10, which gives me a 22. For every variable appearing within the system, he found the subscripted determinant. So, there's an x, he found d sub x. There's a y, we have to find d sub y.
Now, subscript is the one you're going to replace with.
Go ahead. Now, the subscript one is the one, that column that you're going to replace, but you go back to d each time. X is back to being 7, 8. You don't replace this 5, 4 with 3, negative 2. If you did, you just get a determinant of 0. You go back to the original coefficient determinant. That is the one that you'll do the replacing in. X is back to 7, 8. The y column is 3 and negative 2. You're only replacing one column at a time. One of the other column, the one that's not being replaced, is the original values from the coefficient. So we multiply minus multiply. So 7 times negative 2, that's a negative 14, minus, what are we going to have here? 24. Negative 14 minus 24 gives me a negative 38.
Now you're going to write out what Cramer's rule actually says.
Here's what Cramer was able to prove, okay? Cramer was able to prove that the value of x would always equal d sub x divided by the coefficient determinant d. X will always equal d sub x divided by d. D sub x is 22. D is a negative 12. Positive divided by negative, it's going to give me a negative answer. And we can cancel what? A 2 above and below. 22 divided by 2 is 11. And 12 divided by 2 is 6. So we found the value of x.
Now imagine if you were doing elimination or substitution, you would then have to plug this in to
This
find y.
Cramer's rule is very nice if the solutions turn out to be anything other than integers. This is a very nice process because you don't take that and have to plug it back in to find y. To find y, Cramer was able to prove that the value of y would always equal d sub y divided by d. D sub y turned out to be a negative 38. And D turned out to be a negative 12. Realize you better not mess up on D, because you're using the value of D for every answer for the answer to the variables for x and y. If you mess up on D, you're going to get x wrong and you'll get y wrong. Negative divided by negative, that's a positive. Oh, what have we got? We can cancel a 2. 38 divided by 2 is 19, and 12 divided by 2 is 6. So these two lines will intersect at the unique point negative 11,6 for x and positive 19,6 for y.
So
pretty neat, don't you
state
think?
Cramer's rule, it'd be x equals dx over d and y equals dy over d. But what the heck is d, dx, and dy? That's why I didn't just state Cramer's rule. You got to see what that d is. D is the determinant of the coefficient matrix. Dx is the determinant
when you replace the x column with the column of constants. Dy is the determinant you get going back to d. You replace the y column with 3, negative 2. You don't leave 3, negative 2 there for x. The x values went back to their original coefficient values. Any questions there?
Let's see if I can type this in.
If there'd been a z, you'd have to find d sub z and divide it by d.
Parentheses. What was that? A negative
11
over 6. I'm not going to put the comma down there with that 6. It might count it wrong if you do. I'll go right arrow, 6 and 19 over 6.
Yes.
Don't
close parentheses.
Don't put the parentheses. Oops. Don't put the parentheses down there with the 6. Go right arrow, parentheses. There.
Any questions?
Let me get it back to.
This process is extremely easy to program if you're having to program a method to solve a linear system of equations. Look at this work here, okay? Look at my work. There's no time. With elimination and substitution, you ultimately wind up having to solve a linear system, combining like terms, dividing. Here, there's no algebraic manipulation. Look at this. It's all numeric. That's what computers do the best, okay? There's numeric calculations. Multiply, minus, multiply. A very easy process to program if we have any computer programmers out here. And that's one of the things that kept Cramer's rule popular throughout the years. Is it's an easy process to program for solving a linear system. Let's do another one.
Resurrected and showed up here, he'd probably be so upset to know that all he's known for is x is dx over d and y is dy over d. No. But here's another one. And if you're thinking, well, wait, I want to do this one with elimination or substitution.
Would you get the same answer if you used elimination or substitution? Let's see what they say. You better.
Yeah.
There's only one unique point of point of intersection. So if you used elimination or substitution, say on number 13, you'd get the same solution. But hopefully
what
y'all
you're
agree. Hopefully y'all agree that this is nice because you don't have to plug in fractions and then simplify this process.
Just multiply.
Yeah, multiply and divide.
Now get that. Those
Wait, I
constants.
am 4 and 6. 6, 32. Okay.
6, 2, 6.
So we'll start with the coefficient D. The determinant of the coefficient matrix. And once again, you have to have your like variables aligned. They are. You have to have your constants on the right-hand side. They are. So the coefficients for X are 4 and 6. The coefficients for Y are 3 and 2. And then we multiply minus multiply.
Oh my gosh.
What?
It hasn't dawned on you yet.
We get a 4 times 2, that's an 8, minus 6 times 3 is an 18. 8 minus 18 gives me a determinant of negative 10.
Let's see if he realizes why I started laughing.
Yes. Yeah.
Y'all see
Now
what-
we're ready to find which determinant. D sub x.
And when you see what's about to happen, tell me.
We replace the x column with the column of constants, 4 and 6. I think we're about to get the same, aren't we going to get the same matrix here? The x column is replaced with the column of constants. Those constants are the same as the coefficients of x. So we're going to have the same determinant, aren't we? We'll have another 8 minus 18, which is a negative 10.
So we at least know that x is 1. Okay.
Dividing negative 10 by negative 10, we know x is going to be 1. Let's find d sub y. What numbers do I write here? Okay, and it's the black 4, 6, not the red 4, 6. What numbers do I write here? That's the red 4, 6.
And look, this one's really working out easy. Wow.
If you have the same rows and the same columns, or the same column, here we have the same column. If you have identical columns or identical rows, the determinant's going to always reduce to 0. And that's what we're seeing right here. Well, multiply minus multiply, 24 minus 24. Wow, this is pretty nice. Gives me a dy value of 0. So Cramer and his crowning accomplishment. He was able to prove x is always going to equal d sub x divided by d. So negative 10 divided by negative 10 gives us a positive 1. These lines will intersect at an ordered pair where the x coordinate is 1. Now for y, that's d sub y divided by d. 0 divided by negative 10, what's that going to give us? 0. Remember, a number over 0. You can't have a 0 in the denominator. That's undefined. No, that says no, you don't want that. But 0 divided by a non-zero constant, it's okay to have a 0 on top. That's equal to 0. So these lines intersect at the very nice ordered pair, 1, 0. Any questions?
1, 0. Cramer, really? Y'all imagining him sitting around, noticing
Noticing is one thing, proving was the other.
Was the other. Any questions?
Any questions? Now some applications.
We're going to end the
Applications
semester
of
with some
linear
word
systems.
problems. And we're going to skip number 15 for a moment and go on to 16.
We're just going to delay it. We're not skipping. Applications of linear systems. We have three methods of solving linear systems at this point: elimination, substitution, and Cramer's rule. And you're going to find, or you're going to see that my preferred method is elimination, okay? I know, well, Cramer's rule is great because if it's going to be messy fractions especially, then you have to be plugging in those messy fractions to find the value of the other variables. But
let's read through this problem, and you'll tell me if you think your answers are going to be fractions.
A woman bought some large frames for $19 each and some small frames for $6 each at a closeout sale. If she bought 23 frames total for $255, find how many of each type she bought. Now, frames, I think we've decided in the past these are picture frames. I thought of glass frames, frames of glasses, but no, I think they're picture frames. She's probably an artist, and she's framing her pictures, getting ready for a big show or something. Yeah, Zelda. Yeah, okay. You went and you bought those picture frames, getting ready for a big show at a local gallery. Okay, we're going to strike it rich. But do y'all think it'd be sensible for us to say, well, first of all, what are the unknowns? How many of each type? Find how many of each type she bought. When you read that problem, there are two things we don't know. What are they?
The number of frames for
Each frame. How many large frames she bought, and how many small frames she bought. And switch to my paper. This is number 16. I'm going to start making a table.
A procedure to set
for
this
linear
up.
systems. You can summarize the information that they give you using a table, and that's what I'm going to do here. I think there are two unknowns: how many large frames she bought, and how many small frames. I'm making a little table here, and the thing we don't know is the number. I'll say the quantity. How many did she buy? How many of each type? She bought X large frames, we'll say, and Y small frames. Because those are the two numbers we don't know. We'll label them X and Y. They gave us some more information about these picture frames. Oh, those large frames cost $19 each, but the small frames only cost $6 each. So switch back to my paper. You're going to notice I keep going back and forth between my work and the problem itself, reading and taking apart each little piece of information they give us. So I'm going to label this the price per frame. The price per frame. The large frames cost $19. The small frames were only $6.
Is there any other information they give us?
Let's look back. I think they give us some more information.
Oh, okay.
Important information.
Now keep in mind, what we want to do is come up with something that looks like, that.
We want a system of equations. And here's something you may want to remember. If you took a linear algebra course, you would learn that the number of, if you want a unique solution, then that means not a situation where there are infinitely many solutions or no solution. If you want a unique solution, the number of unique equations has to equal the number of variables. We have two variables, so we're going to have to come up with two unique equations along the way. Look back at the problem.
What have we not used?
They give us some totals. she bought a total of 23 frames. Switch back to my 23 is a total of the number of frames, the quantity. If you take, she bought X large and Y small. If you total those two, it'll better equal 23 frames total. Any questions on my logic there? Because once we get this table made, we'll have the equations almost just staring at us.
Like, could she have bought 10 large and 10 small? No.
Because it has to total 23. Next, the price, they give us the price. We have the large frames cost $19. Small frames cost $6. How much money did she spend? Let's total up the amount of money that was spent. She spent, what does the problem say? $255 on these frames. She spent $255. Any questions on our logic? We totaled up the quantities, we totaled up the dollar amounts, and one equation falls out immediately. We need two. If we take the number of large frames she bought and add it to the number of small frames she bought, that'd better equal the 23 frames that she bought for the on the sale. Now the second equation is the cost quantity. I refer to it as a cost quantity equation. Let's stop and think. Suppose she bought 10 large frames. How much money total did she spend on those 10 large frames? I chose 10 because that's an easy number to work with. Each large frame was $19. How much did she spend on those 10 large frames total? $190. How did you get that? You take the price per frame and multiply it by the number of frames she bought. Well, in this case, the price per frame is $19. She bought X frames, so 19 times X. That's all the money she spent buying the large frames. This 19X is the total amount spent on the large frames. Amount spent on the large frames. If you understand that, then you can tell me how much money she's going to spend on the small frames. Each small frame costs $6. She bought Y small frames. So total, how much did she spend on those small frames? Not 6X, 6Y. Right. Here's a recurring theme in these problems. It's the price per quantity times the number of times the quantity. She spent $6 per frame times the number of frames. And I'm going to make a note that 6Y, that's the amount that she spent on the small frames.
I remember years and years ago, I had a student that just could not get over putting the 23 and the 255 here. He wanted to put the 23 right here, right where my mouse is, and the 255 right there. And clearly he didn't understand what we were doing. These are totals. Did you ever have anyone wanting to do that? The 23 here. Why can't I put the 23 here? Well, it doesn't make sense to put it there. The 23 is not the total of large frames.
Okay, the amount spent on the large frames plus the amount spent on the small frames had better equal what? 255.
Now, are you going to clean that up?
Yes, I am. So here we have two unique variables. We have two unique equations. Now, reason I say unique equations, you can't just come up with one equation and then decide, oh, I'm going to multiply everything through by 2 and get 2x plus 2y equals 46. There's my second equation. No, they have to be different equations. So here's what we're going to have to solve. X plus y equals 23, and 19x plus 6y equals 255. At this point, I guess we could use Cramer's rule, but I don't think I'm going to.
What's your favorite method, Tim?
Elimination, so I'm going to use elimination. Unfortunately, we don't have the same coefficient for any like variables. Here we have a 1 and a 19 on x. Here we have a 1 and a 6 on y. I'm going to have to get the same coefficient but opposite sides. I'm going to go with the one, I'm going to work with the one that has the smaller coefficient. That's 6 right there. I'm going to change this 1 to a negative 6 by multiplying the first equation by negative 6. The second equation is staying as it is. It's a 19x plus 6y equals 255. That first equation, we're multiplying 3 by negative 6. What are we going to get? There. We'll have, I'll get us started. We have a negative 6x. What else?
Negative 6y.
Okay, that negative 6 times 1y becomes that negative 6y. Negative 6 times 23. Is that a negative 132? Y'all, no, 138.
It's
Negative
120 plus
138. If we add these two equations together, let's add the two together. What are we going to get here when we add the x terms? We have a negative 6x plus 19x. That's going to give me a 13x. And what's about to happen to the y terms? That's why they call this elimination. Those things are gone.
You made it.
I made them leave, okay? By multiplying 3 by negative 6 and adding them together. Negative 138 plus 255 is going to give me a... I couldn't hear you? Positive 117. Now, remember, x is representing the number of large frames that this artist bought. Would it make sense for me to get an x equals negative 4? Would that be acceptable? No. We can't get a negative. What about a decimal fraction? Would that make sense? No, she can't buy half a frame or a third of a frame. We better have counting numbers as our solutions. If this is going to have any meaning to it, we better get a counting number here. So divide by 13 to give us x equals, let's see, is it, don't tell me 9? I'm getting 9 large frames.
And at this point, they could just, hey, make a new copy.
There it is. Oh, let me lower it.
No.
We now know the value of x. It's 9. Or 9, the rest, that means all the other frames have to be small frames. You can just stop and think your way through. What does y have to equal? You know that x plus y has to be 23. 9 plus what gives you 23? 14. So Zelda, I see that she specializes in small art pieces, so she bought more small frames than large frames. Any questions there? Or you do with elimination, remember we substitute back in, choose the one that's the easiest. I think x plus y equals 23 looks the easiest, so you plugged in the 9 for x, subtract 9 from both sides, so algebraically we get 14 also. So whether you think about it the way we did right here, or back substitute to get the value of the other variable, either way, you'll get the same answer. 9 large, 14 small frames.
Oh no, we're about to, no, I don't want to leave that side. So 9 large, oops, and
14 small.
Is she getting 23 frames altogether? Yep, she sure is.
Any questions there? This concept that we used to get the second equation is a recurring theme in these problems. You'll be given some information about a single unit, and that numeric information times the quantity. In this case, price times quantity tells you how much you spend on all the large frames. Price times quantity tells you how much you spend on the small frames. Any questions there? Number 17.
So the way on the next one, instead of large frames, small frames, it's going to say something else.
The cost to attend a movie is $5 for adults, while children are admitted for only $2. If a movie was attended by 62 people who paid a total of $169, how many adults and how many children attended the movie? Number 17. Okay, let's start. Reread that.
You know what, Tim? Why don't you draw that second column, the XY column first?
Do what?
Make the XY column. Leave room for the unknown. Draw the XY.
So this is, well, first of all, they need to look and tell me what is the unknown here? What do we not know? How many unknowns do we have?
Yeah.
2 unknowns. Those boxes are telling you what the unknowns are. You need to know how many adult tickets were sold and how many children tickets. So I'll say adults and children and I'll let the unknown column, that's the number of tickets. We don't know how many adult tickets were sold. We don't know how many children tickets are sold. They gave us some more information. I think they gave us the cost of each ticket. I'll say cost per ticket. Adult tickets cost $5.
How much for the
Children tickets were only $2. So we have adult tickets and children tickets. The adult tickets cost $5, children cost $2. If a movie was attended by 62 people and they paid a total of $169, how many adults and how many children attended the movie? 62. That sounds like a total. Switch back to my paper. Where do y'all think I'm going to put that total of 62? Where will I put the total? Under the variables. You have X adult tickets plus Y children tickets. Total those up, add them up, and that should be 62 tickets. We know the price per ticket, so let's go through that logic. Suppose 10 people attended 10 adults attended that movie. How much money did the theater get from those adult tickets? If X is 10, how much money did they get from those 10 adult tickets? $50. So once again, you're saying price times quantity will give us the amount of money spent on adult tickets. Price times quantity will give us the amount of money spent on the children tickets. And they spend a total of, what did it say?
$169.
And I see my two unique equations falling out from how I summarize this information. Take the number of adult tickets plus the number of children tickets. That'll better give us the 62 tickets that we needed. What about my cost quantity equation? What would that be? How much money did they spend on the X adult tickets?
How much money did they get, not spend?
Yeah, well, the adults spent it, but how much did the theater get from the X adult tickets? It's $5 per ticket. They sold X tickets.
No, 5X.
5X. That's the price per item times the number of items plus how much money did they get from all of the children tickets they sold. They sold Y children tickets at $2 each. 2Y, and that has to equal the amount of money that they took in, $169. Any questions? Because once you get the system of equations set up, it's just a matter of elimination, substitution, or Cramer's rule. I'm going to go with elimination because this shouldn't be fractions. If I thought I were going to get fractions, I'd use Cramer's rule. But I shouldn't get fractions. They can't sell a third of an adult ticket. So, y'all tell me, which letter do you think you want to eliminate? Do you want to eliminate X or do you want to eliminate Y? I'll do the one that y'all want me to do. X. Now, if we're going to eliminate X, what would we have to multiply by? We need this number here to be -5. So what do we have to multiply by? Okay. If we'd eliminated Y, what would we have to multiply by? Yeah, so do you want, Alex, do you want to stick with X? I'm fine either way. I think Y would be easier just because the number is smaller, 2 versus 5. So if it's all the same to y'all, it's like when I let friends choose where we go out to lunch. They get to choose the restaurant. If they choose the wrong place, they get to choose again. They can just keep choosing until they choose the right place. Okay, so we're multiplying through by -2.
Unless they're paid.
How often does that happen?
It's about to happen this evening.
How do you know?
Well,
okay, distributing the -2, what are we going to get? Y'all just call out that rewritten, the first equation. What will it give us? -2x, keep going. Minus 2y equals, okay. Multiply by -2, multiply by -2, multiply by -2. Now the second equation isn't changing. It stays at 5x plus 2y equals 169. Let's add those two equations together. Combining the x terms, what's that going to give us? 3x -2y plus 2y. That's canceled out. It's gone. We have eliminated the y variable. -124 plus 169, that gives us a positive 45. Divide both sides by 3. 45 divided by 3 gives me 15 adult or children tickets. Which one? Adult. Remember, X is the number of adult tickets. So 15 adult tickets.
You can make a column over here that says answer. I know one semester we did that.
Yeah, but I like doing it like this. I like putting it right here. Can y'all read that? We now know the X value, it's 15. Well, if there were 15 adult tickets, that means all the rest of them are children tickets. 15 plus what will give us 62? Okay. Or you can do what we were doing the last time. Substitute. You could substitute into either equation, but use the one that's the smallest. Has the smallest numbers. X is 15, so 15 plus y equals 62. Subtract the 15, 62 minus 15. Algebraically, we get 47 children tickets, but I like just thinking about it also. So that means there are 15, they sold 15 adult tickets and 47 children's tickets.
And look, that's sort of an outline on how to do these. You have your unknowns, your variables, and then there better be, if there's two variables, there better be two equations.
Two unique equations.
Mm-hmm.
Once again, I say two unique equations because you can't just find the first equation. Oh, there's x plus y equals 62 is my first one. Now I'll multiply by 2. 2x plus 2y is 124. No, that's just the same equation multiplied through by a factor of 2. You need two different equations if you're going to have a unique solution. Any questions there?
I think with just the way
Tony,
these
you wanna
problems are
do-
worded, there's no way they're going to say,
You want to do the last two?
no, you go ahead.
Okay.
It'll keep things moving faster. But there's no way you're going to have
18. I think someone
Think
had to
about
leave
the many
early.
questions.
Yeah,
I
at
know.
least you've seen.
yeah. Mhm.
If you're if you have to leave early, at least you've seen what we were doing today.
Oh, poor Mike.
And they give it the Gaussian elimination. They use that terminology.
Ignore
No,
this,
we're
right.
using Cramer's rule. Okay.
No, we're using elimination.
Oh, we're using elimination, not Gauss-Jordan elimination. We're just using
Gauss-Jordan elimination is when you punch it in your calculator and get those ones and zeros down the diagonal. We're not doing that. Okay?
Oh, we're ending up the semester. Here, this is sort of a downbeat problem. Mike works a total of 58 hours per week at his two jobs. He makes $7 per hour at job A and $8 per hour at job B. If his total pay for 1 week is $427 before taxes, then how many hours does he work at each job? I remember this problem once. He was working 84 hours a week. Oh, I felt so sorry for poor Mike. But what are our unknowns? What do we not know? The way they phrase the questions and the way they want the answer, they're sort of telling us what those unknowns are. But I want to hear someone tell me. What do we not know about this problem?
What are you going to label for unknown 1 and unknown 2?
Yeah. For unknown 1 and unknown 2, what am I going to write there?
Job A.
Job A and job B. Mike has two different jobs. So job A and job B. And the thing we don't know, I'll label X and Y. That's the number of hours he works each week. The number of hours. I remember a student telling me he makes $7 an hour on job A and $8 an hour on job B. I remember a student saying, well, he should just quit job A and do all 58 hours at job B. It doesn't work like that. You can't go and tell your boss, oh, I'm just going to work 58 hours here and make more money per hour. Unfortunately, it doesn't work like that. So here's his hourly, I'll label the column hourly wage He's making $7 per hour at job A and $8 per hour at job B.
Now we need those totals.
There should be some totals somewhere.
Hopefully you're noticing a pattern on these.
I said no, but it's consistent. I said it's consistent, even though they're not noticing a pattern, but it's consistent.
What are the 2 hours? The 2 totals.
We need some totals. He works a total of 58 hours per week, and he made $427 before taxes.
Where
So-
would you put the 58 and where are you going to put the 427? Tell us.
Okay, where will we put the 58 hours that he worked?
Under the
Okay, under the variables, he worked a total of 58 hours. And what was the, how much did he make?
427.
Okay, that means the dollar amount. You'll notice when working with these dollar amounts, here's something you might want to remember. The dollar amount always goes under the dollar column. It wouldn't make sense for you to take a number of hours plus a number of hours and it give you a number of dollars. Hours plus hours is going to equal hours. So, and what was the total? I forget again.
427.
427. Okay, we have 2 unique variables, so we need 2 unique equations. Call out one for me.
X plus Y is 58.
X
Perfect.
plus Y is equal to 58, I agree. And a second equation. Did my battery die? I think it did.
Hear anything?
No, it's
No.
dead, isn't it?
Oh. No.
Uh-oh.
If
Yeah.
I can find it back.
Oh, it's dead.
Oh, shoot. You keep going, Tim. Just talk loud.
Okay, y'all tell me the second equation.
8X plus 9Y equals 427.
Those are your numbers. Did you hear Alex saying 8x plus 9y? He's using his own numbers. Our numbers would be 7x plus, what am I? Oh, that's you. Plus 8y equals 427. Well, y'all know I prefer elimination, so what do y'all think I'm going to do? Am I going to eliminate x or am I going to eliminate y? And that doesn't matter to me. Y'all just tell me. Which one do you want to get?
I always eliminate the smaller number.
No, the smaller coefficient. So, but that doesn't matter. I'm going to let them tell me. X, you want to eliminate x? To eliminate x, we're going to have to multiply this equation by -7. Remember, you want the same number but opposite signs. So we can multiply that first equation through by -7. That's going to give me here, here, here. That's a -7x minus 7y equals, 50 times 7 is 350. 8 times 7 is 56. So we have 350. I'm getting a -406. Someone check me with their calculator.
Oh, I did
Yes.
it in my mind, so you don't even have to use it.
And then we have that second equation.
Oh, this is going to work out nice.
Add the two equations together. -7x plus 7x. Okay, so that's gone. -7y plus 8y gives me 1y equals -406 plus 427 gives me 21 hours at job B. Y is job B, the number of hours worked at job B. We solved for Y, so we know Mike was working 21 hours at job B.
How many at job?
How many hours did he work at job A? Okay, you need it to add up to 58. 58 minus 21 gives us 37. Or, as I said, you can just substitute in x plus y is equal to 58. Y is 21. Subtract 21 to get x equals 37. Either way, you get 21 hours at job B and 37 hours at job A. Of course, if Mike were able to work all 56 hours at job B, 58 hours at job B, he'd come out ahead, but in the real world, it just doesn't work out like that.
So
you can't
37
for job A and 21 for job B.
Okay, and there's still one we haven't done. Go back
It
to
follows the
15.
same pattern. It's just the the wording, the way I have to say this, okay? That a basketball player scored 27 times during one game. She scored a total of 42 points, 2 points for each 2-point shot, and 1 point for each free throw. I remember that from PE in middle school and junior high. Let's see, you had your 2-point shots and you had your free throws, and the free throws were only 1 point because they're easier, that people aren't trying to stop you there, okay? You're standing there still at the little line with your free throw, so they're only worth 1 point. I can speak with great knowledge of basketball from my time playing basketball in middle school, yes.
So what are the two unknowns?
We need to know our unknowns. What are the unknowns? A basketball player scored 27 times during one game. She scored a total of 42 points. She got 2 points for each 2-point throw and 1 point for each free throw. How many 2-point shots did she make? How many free throws did she make? What am I going to write? Here's my table. I'm going to start my table. What am I going to use as row headers? That's where I put my unknowns. The 2-point shots and the free throws. And we don't know how many she got. Those are the unknowns. So I'll say number of shots scored. She scored X 2-point shots and she got Y free throws. She made X 2-point shots and Y free throws.
And
those are 1
next
point
column
shots.
is not a dollar column.
No, it is not a dollar column. They give us information regarding one individual item. 1 2-point shot was worth 2 points. 1 free throw was worth 1 point. This is the points per shot. Not the dollars per item, but the points per shot. Just like over here, where we're dealing with dollar amounts, 1 item, 1 hour, he was paid $7. 1 hour, he was paid $8. Here, 1 2-point shot was worth 2 points. 1 free throw was worth 1 point. We need some totals. We have to come up with the equation, something equals. So we better have some totals. Go back to the problem. Let's look at it again. She scored a total of 27 times. Where's that 27 going to go? Is 27 the number of points she got?
What's the number of points?
Number of points is 42. Switch back to my paper. I'll let them tell me where I'm going to put those numbers. I got to put 27 somewhere, and I got to put 42 somewhere. Where will I put the 27?
Under the variable.
Okay. Number of 2 points plus number of free throws. She scored 27 times. Now, adding up the total number of points. The total number of points was 42. Was it 42
Yes.
points? So, I need two equations. What will those two equations be? First,
X plus Y equals 42.
okay, x plus y. Now I think it's 27. X plus y.
Yes.
Oh yeah, is equal to 27. And now we need another equation.
2x
Okay, points per shot times the number of shots
plus Y equals
plus points per shot times the number of shot equals 42. Any questions on our logic there? This is actually really a nice first question. Maybe we should have done it first. I just didn't know that
I
it
don't
showed
like the
the pattern.
2-point shots are worth 2 points.
They need to call 2-point shots something. They're not free, which means you have to pay for them. So paid shots and paid throws
Okay,
and
Tim,
free throws.
We're not going
maybe.
to change basketball terminology. So
Well, once I take over the world, maybe I'll add that to my list. Okay, I'm waiting for y'all to tell me what to do. There's one variable that would be the quickest, easiest one to eliminate. Which one would be the easiest one to eliminate, X or Y? Y, I agree. We have a 1Y and a 1Y. All we need is for one of those to be a negative 1. I'm going to multiply that first equation by negative 1. That'll give me a negative 1x. What else? We're having to distribute. Okay, equals. And that second equation is not changing. 2x plus y is equal to 42. Adding the two together, negative 1x plus 2x gives me x. What's about to happen to the y's? So, negative 27 plus 42, is that a positive 15? And so x, that's the 2-point throws. So this player scored 15 2-point throws. She scored 15 2-point throws. What does y have to be? How many free throws did she get? 27 minus 15, I agree with 12. 12 free throws.
Plugged in a 15.
Any questions there?
I'm touching these answers because we said we'd make it fast today. So 15 2 points and 12 free throws. 15 2 points and 12 free throws. Okay, all together, 27 and, oh wait, I clicked that. We've done them all. Any questions? These word problems sort of follow a pattern. Y'all see that?
If you're a business major and you have to take Math 1324, you'll do a lot more with this stuff, okay?
A lot of really good business
applications involving linear systems.
Any questions before I stop recording?